All right, this is my review for exam 1, chapters 1, 2, and 3, specifically chapter 2. We spent almost all of our time in 2.1. And this is really where our material comes from the chapter 2 material. If it was a face-to-face class, we might do a couple of more things there. The 2.2 material is reasonably handled a little bit later in the semester, so I don't stress about that too much. But it's really about frequency distributions. That was the first thing we encountered. They're going to be with us for the balance of the semester. They take a couple of different forms depending on the topic at hand. But basically, we've got our class or category on the left, our frequency or count on the right. So that's your basic frequency distribution. Now, a little bit about the vocabulary here, because honestly, it's really about understanding the vocabulary out of chapter 2. So there's a couple of things that do puzzle students, so I'm going to go through them and I'll offer up examples and try to clarify. So, lower class boundary. Oh, excuse me. I'm going to start that over again. It's lower class limit. Sorry. Try that again. Here we go. Ooh, lower class limit. I always abbreviate it LCL, and that is the smallest possible value in a class. There's no guarantee that one of those smallest possible values for that particular class is actually in there. It's just the cutoff. Nothing smaller than that. That's as small as they can get. The lower class limit has a friend. That's the upper class limit. And that, as you might expect, is the largest possible value in a class. So again, there's no guarantee that one of those values is in those classes or that class, but the lower class limit and then the upper class limit, LCL and UCL, are the first of the vocabulary terms we use to define the bits and pieces of our frequency distribution. Class boundaries. This one, it's going to be a bit puzzling to students. Even if you kind of get it, there's still one or two areas that may be a bit puzzling. So I'm going to offer up a very specific example here. Maybe even two, who knows? Let's see. So class boundary, these are values that separate the classes. And this is the important part. Without being, excuse me, try that again, without being part of any class. So let me show you what I mean by that. I have no idea what we're measuring. Oh, let's measure time in minutes. We've got our frequency F. I could care less about the frequencies for this discussion, because it's really not about them. It's really about what happens over here. So 0, 10, 20, 30, 9, 19, 29, and 39. One thing that I hope people have noted about the notion of class is that they don't, like butt up exactly against each other. One class ends before the next class begins. So the first class ends at 9, the second one begins at 10. There's a gap in between there, and that gap is quite specific. That is the gap that we look to when we're trying to determine what the class boundary between the first and the second class is. So 9.5 is the class boundary for the value that's halfway between 9 and 10. And we do that for all of them. So we'll do that for each of these pairs. So just like we've been doing here, I've got a 9.5, I've got a class boundary at 19.5. I've got another class boundary at 29.5. So it's very possible to really get that right away and be very hip to that, and not yet realize that there is another 2 class boundaries for this table. There is a class boundary that instantiates or begins the first class. So there's an initial class boundary. There is also a class boundary that ends or finishes the final class, some value out here. You can see that these class boundaries are not even part, per se, of the table. The first class boundary, since we began here at 0, and we've been going by 0.5, that first class boundary is a negative 0.5 for that first class boundary. Notice that negative value there. That's significant for that first class boundary. That's because we've got the 0 over here. Following the same sort of logic, we've got a final class boundary of 39.5, because that's the way the class boundaries have been running. So that final class boundary in this table, or for this table, I should say, is 39.5. And again, it's because of that little guy there. So that's something that can get missed, these first and last class boundaries. Honestly, some of these frequency distributions don't necessarily have a class boundary at either end or both ends. I'll let you think about that. But class boundaries. So, as I say, class boundaries, or CB, can be a tricky little thing. Class midpoint. I like CM for that. This is the value halfway between the upper class limit and the lower class limit. This one actually has a formula. The class midpoint, UCL plus LCL all over 2. Since addition is commutative, it works in the other direction also. You need both an upper and a lower class limit clearly for this definition to work, but in reality, it's not a very difficult calculation to make. I'll run through a very quick example here using some of the data from that previous table. Let's see, class number 2 went from 10 to 19 with some frequency. So the class midpoint is equal to 19 plus 10 divided by 2. That's 29 divided by 2, or 14.5. So the class midpoint is equal to 14.5. And you can see that it's exactly halfway between the 10 and the 19. So that is your class midpoint. It's one of the few out of this first couple of chapters that actually requires some sort of formula. This formula gets used an awful lot with different bits and pieces. There's a lot of times we need to find a number halfway between two other numbers. The context will change the notation a bit, but not the formula. So let's see. And then the last one is the class width. This here, again, is another one that can confuse students. And I think it is because most students will come to this particular definition with the assumption they know what it means or what they want it to mean. Class width, it is a difference. That means A minus B between, and this is what gets confusing, is because there's two statements for this particular definition. It's a difference between consecutive upper or lower class limits. And it's important to realize that when you calculate class width, you are supposed to use consecutive upper or lower class limits. It's the consecutive part that's really, really important. It's what really sets the definition. And unfortunately, I think it's something that tends to confuse students. Let me offer up an example. If I go back to that last one, I don't care again about the counts, not now, not for this. So those are my class limits right there. So it says consecutive upper or lower class limits. So here's how this has to work for us. For my first class, if I want to find the width for that first class, I need to take and work with consecutive upper or lower class limits. This time I'm going to work with consecutive lower class limits. So 10 minus 0 equals 10. When I get to the second class, I'm going to use consecutive lower class limits again. You can already see that these classes are going to have the same width just because of the way they look. But if I ask you on an exam, you want to be able to answer the question correctly. So now when I get to the third class, color? Yes, I do. Again, I'll use consecutive lower class limits. So I've got 30 minus 20 or 10. And then we come to the reason for the kind of bifurcated, if you will, definition. When I come to the last class, the rule I've been using so far has a bit of an issue. If I try to use consecutive lower class limits, there's not another consecutive lower class limits. That is why for the last class, I use consecutive upper class limits. So this 39 minus 29 equals 10. So this is why we've got the kind of crazy definition for class width. And as I say, it is also, I think, part of the reason that students struggle with this is that you guys come with some baggage as far as what you want class width to be. Most people, if they're asked what it should be, they'll tell you it should be a difference in upper and lower class limits. But it is most definitely not UCL minus LCL. It is not equal to that, not in any way, shape, or form. So be very aware of that. People like to think it's that all the time. That's what we want it to be. It's nice, it's great, it's simple, but no, it's not correct. So you want to keep that in mind when you come into contact with the notion of class width. So those are the main definitions for your frequency distribution. We introduced a couple of other distributions based on a frequency distribution. We have the relative frequency distribution. Basically, your counts are presented as proportions. So let me go ahead and run through an example. This time I do want my frequencies in there. I'm going to continue to use the same frequency distribution I've been using. It's just a little bit easier there. So 1, 7, 12, 9, and sorry, so 2, 7, 12, 9, and 3. All right. So that's your frequency distribution. If we want the relative frequency, I've got to sum those x's. This is the class, by the way. If I sum those x's, let's see. 7 and 2 are 9, 9 and 9 are 18, 18 and 12 are 30, and 3 are 33. So to calculate the relative frequency, and I'll run through this on my calculator. You won't need to see me demonstrate it. It's really straightforward. To calculate the relative frequency, I'll take each class count and I'll divide it by the total amount. Rounding can vary. But your calculator will find these at the drop of a hat. We never have so many, by the way, that we, and by the way, I'm going to round these to 3 decimal places. I usually provide the rounding rule for this type of thing. So 0.061. 0.212. 0.364. I'm rounding as I go. If you're doing this on your calculator, you'll be seeing numbers that need to be rounded. 0.273. And then 0.91, 0.09. You may see these presented in terms of percentages, in which case you have 6.1%, 21.2%, 36, I said 36.4%, 27.3%, and 9.1%. So, by the way, if you add up all of these, they should sum to very close to 1. They may not be exactly 1 because you've done some rounding, but they'll be very, 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 very close. So that relative frequency requires that we find the class, the total count, and then we divide each class count by the total count, and there's usually rounding involved. So that's your relative frequency distribution. Your relative frequency distribution has a friend. All right, cumulative frequency distribution. The definition here. This is the class count plus all previous class counts. And I'll go ahead and use that data again. So 0, 10, 20, 30, 9, 19, 29, 39. Those are my classes. And these are my frequencies. So what were they? 2, 7, 12, 9, and 3. Which one did I leave out? 1, 2, 3, 4. Oh, so I'm sorry. 1, 2, 3, 4. I didn't. Oh, I had an extra one in there. Gosh, I just realized that. Okay, there we go. That was my bad. I should redo that previous screen. In fact, I will. It's going to be terrible. For some reason, I threw an extra 3 in there, so that's not a problem. 40 to 49. Yeah, that one's a little different. There we go. I'm sorry about that. It actually works better for my next example. Let me squeeze him in there. 40 to 49. 30. There we go. Now I'm more happy. All right. I apologize for that. All right, so now my cumulative frequency. It's all about adding in previous counts. For the first class, there are no previous class counts. So it is literally 2. For the second class, it's 2 plus 7 or 9. 2 plus 7 plus 12 equals, let's see, 9 and 12 is 19, 21. Then we'll have literally 2 plus 7 plus 12 plus 9, which is 30. And then finally, we'll have 2 plus 7 plus 12 plus 9 plus 3, or 33. So those are the cumulative frequencies. 30, 21, 2. So there we go. For some reason, students do find this a little bit puzzling. I'm not quite sure why. Cumulative, you want to think of the process of accumulation, adding as we go. Okay. So I'm going to go ahead and hopefully that will help there. So we've got three flavors of distribution. We have the frequency distribution with the straight counts. We have the relative frequency distribution, where the same counts are just really presented in terms of a proportion or possibly a percentage of a whole. And then the final version, the cumulative frequency distribution, where we actually add in counts as we go up the class level. Now, there's one other topic out of this section that bears discussion. Normal or bell-shaped distribution. All right, so the technical phrase is normal. We start with bell-shaped, mostly because that's what people understand. A bell is shaped like this in the land of statistics. We've got classes on the horizontal. We've got counts or possibly relative frequencies on the vertical. So this is very much a graph, very much like you used to work with in algebra, with some differences and some similarities. But a normal distribution has the following properties. So let me put the data that we've been working with back up here. Those are my classes. These are my frequencies, 0, 10, 20, 30, 40, 9, 19, 29, 29, 41. And then what do we have? We had 2, 7, 12, 9, and 3. Now, if I were to convert this to and we did not do much of this because it does not honestly work very well with your TI-84. It might work better with some other tools, but it's also so visual, and it can be really tedious to get the calculator to do what we want to do. I really don't cover this all that much. And don't worry, it doesn't sneak up on you in exams. If I do a histogram, down below I have my class boundaries. The class boundaries actually serve to separate the classes. So I don't have enough room there. Yeah. I'll do it backwards. So you end up with a histogram, what is often referred to as a bar chart, that looks somewhat like this. I'm futzing it a little bit, but we've got our class boundaries on the horizontal. We've got your frequency count on the vertical. So you've got your 2, your 7, your 12, your 9, and your 3. We'll put them in there. Class boundaries serve to separate the classes. And you end up with a picture like this, a histogram like this. And it follows this bell-shaped curve. Not exactly, but pretty gosh darn close. Nature's messy, nothing's ever exact. But a normal distribution has the following properties. Number one, your counts, they follow a low, high, low pattern. You have 1 or 2 major high classes in the middle, and it falls off to lower classes on each end. And that's the first thing, and it is approximately symmetric. So those two things, 1, 2, are the requirements for a normal distribution. There are strict mathematical requirements, but hey, today's not the day for that. So there are two requirements. So when I ask, is this a normal distribution, or does this data approximate a normal distribution, we want to look at this frequency there and see if it follows that particular pattern. So what we can say is, we can say that the data is approximately normal, or if you just say normal, that's okay also. But it's a recognition thing. And by the way, when I give you data in tables such as this, and I ask you a question like this, is it normal? It won't be a real guessing game. The things that are not normal will look really different from normal distributions. The things that are normal distributions will be readily identifiable, provided you look for these two things. You don't need the histogram, but if you look for these two things, that's what will tell you what you've got to work with. Okay, so let's see. That pretty much brings me to the end of the material I intend to cover out of chapter 2. So let me go ahead and end this recording. Before I end this recording, I will ask, are there any questions? Are there any questions regarding the material from chapter 2? You can put them into the chat. I see nothing there right now. Don't worry, if you get it in there a little bit later, we'll come back to it. Don't worry. So let me go ahead and let me switch back over to my camera. I finally got my filter working right. I just like the black and white look. So that's the material from chapter 1. That's the material from chapter 2. If you've been here for the last couple nights, I'm going to cover some of the material from chapter 3 now. And then